So mesh analysis is very similar to nodal analysis in as much as we're going to be setting up a system of equations in order to solve for all involved quantities. But instead of using multiple applications of Kirchhoff's current law, we're going to wind up using multiple applications of Kirchhoff's voltage law. Okay. So I'm going to present this to you guys much like I did with nodal analysis. We are going to go through a step-by-step process. And once again, if you follow the steps in the order that I'm telling you to do them, which that's an incredibly important part, you will wind up getting the right answer every time. Okay. So I'm going to make up a quick circuit here, and I'm going to start with only voltage sources because current sources make us have to modify things. So we'll start learning the basics with only voltage sources, and then we'll introduce current sources in our second example. Okay. So let's say that I have the following circuit. So we've got a 12-volt source, a 10 ohm resistor, a 6 ohm resistor. Let's make this a current controlled voltage source. 3ix. Let's make this a 15 ohm resistor, a 20 ohm resistor, and over here maybe a 4 ohm resistor. And I am going to choose to define my controlling variable current, Ix, as the current flowing down through this 15 ohm resistor. So I'm actually going to lump steps 1 and steps 2 together. So step 1 is really just to identify our meshes, and step 2 is to label our mesh currents. I'm just going to call that one thing. Okay. So steps number 1 and 2 together are identify and label all mesh currents. So on the very first day of class, we talked about what a definition for a mesh is. So a mesh is just any closed loop which can't contain any smaller closed loops. So in this case, all 3 of these little squares would be considered our meshes, and I am just going to assign a mesh current to each of those. Okay. So over here on the left, I might have a mesh current IA. Over here on in the middle, I might have a mesh current IB. And over here on the right, I might have a mesh current IC. So let me explain briefly what these mesh currents are. Okay. So our mesh current IA is essentially the exact same thing as, sorry, let me draw it in red here. The current that's flowing through this 10 ohm resistor. Our mesh current IB would be the same thing as the current that's flowing through that 3ix source from left to right. And our mesh current IC would be the current that's flowing through the 20 ohm resistor from left to right, or through the 4 ohm resistor from top to bottom. Okay. Whenever we have these elements like the 6 ohm resistor and the 15 ohm resistor that are shared between 2 meshes, what we're going to see is that the total current that's flowing through those elements is going to be a combination of those mesh currents. Okay. I have purposefully defined all of my mesh currents to flow in a clockwise direction around each one of those small square paths. Okay. We don't have to choose a clockwise direction. We could choose counterclockwise, or we could choose some as clockwise and some as counterclockwise. It just makes the math a little bit more difficult to follow. I will always set up my mesh currents in this way, flowing clockwise around these loops. You guys can do whatever you feel most comfortable with. I think the kind of circular arrow thing for the second moment of inertia for you mechanical students is in the opposite direction. So sometimes I believe MEs choose to go the opposite way around. It literally doesn't matter. As long as you indicate a current that is flowing around that loop in whatever direction you choose, things are going to work out okay. All right, so we've got steps 1 and 2 taken care of. So our next step is going to be about our controlling variables. So step number 3 is going to be to express our controlling variables in terms of our mesh currents. Okay. So in this system, our controlling variable is the current IX that's defined as flowing down through the 15 ohm resistor, okay? So what we're going to do here is kind of similar to how we define voltages in nodal analysis. So in nodal analysis, I always said that the voltage was going to be equal to the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. Here in mesh analysis, we're going to see that the current will be equal to the mesh current that's flowing in the same direction minus the mesh current that's flowing in the opposite direction, okay? So what I mean by that specifically is as we follow that mesh current IB around its clockwise path, when it hits that branch containing the 15 ohm resistor, IB is going to be flowing down. That is in the same direction as the arrow that's indicating the direction of IX. So we're going to have IX is equal to IB because that 15 ohm resistor is between meshes B and C. Now we also need to figure out what contribution C is going to have, okay? So as we follow C around its clockwise path, when it hits that 15 ohm resistor, it's going to be flowing up. Up is in the opposite direction of IX, so we're going to have a minus sign for IA. So just to recap really quickly here, anytime we're expressing a current in terms of our mesh currents, it's going to be the mesh current that is in the same direction minus the mesh current that is in the opposite direction. Anybody? Yes, ma'am. Oh, goodness. Yes. Thank you, Teresa. That was just a total brain fart on my part. I think I said C and wrote down A. So thank you very much. Yeah, that should definitely be C, IB minus IC because we're talking about the 15 ohm resistor. The one that I just drew actually would have been the current flowing up through the 6 ohm resistor. But anyway, sorry about that brain fart. Thank you very much, Teresa. Any other questions not regarding my asinine mistake? So just conceptually or anything like that. All right. So the next thing that we are going to do is we are going to write a KVL equation for each mesh. Okay. So I have 3 different meshes here, so I'm going to wind up with 3 different KVL equations. When I'm applying KVL at mesh A, I'm just going to follow that mesh current IA around its clockwise path. So essentially, I should see that all of my IA terms are going to have a positive sign, and then any current that's flowing in the opposite direction of IA will wind up getting a negative sign, okay? So for our KVL at mesh A relationship, we should have something like this, okay? So the first thing that I see is the negative polarity terminal of our 12-volt source. So I'm going to have minus 12 volts. The next thing I see is the 10 ohm resistor. The only current that's flowing through the 10 ohm resistor is that mesh current IA. So I'll just have IA. And then the next thing I see is my 6 ohm resistor. Our 6 ohm resistor has 2 mesh currents flowing through it. IA is flowing down through it, and IB is flowing up through it. Since we're following IA around, this combination of mesh currents is going to look like IA minus IB. And now we're back to the node we started from, so we just set this equal to 0. So before I move on to mesh B, where I'm going to ask for you guys' input, does anybody have any questions about how I wrote that KVL equation? All right. So when we perform KVL at mesh B, we're going to follow IB around, and any current that is flowing in the opposite direction of IB is going to get a minus sign. So starting at the bottom left-hand corner, which is what I like to do, somebody tell me what my first term in this relationship should be. 6 ohms times IB minus IA. Great job. Somebody tell me what comes next. Brendan. We're following IB around, so IB is always going to be positive. Anything opposite IB will be negative when we're performing KVL at mesh B. All right, so what do we see after the 6 ohm resistor as we follow IB around? The 3ix voltage source, we see the positive terminal first, so plus 3ix. What do we see next? 15 ohm resistor, and what's the total current flowing through the 15 ohm resistor? IB minus IC. There we go. And lastly, we're going to write our KVL equation at mesh C. So what's the first thing we see when we're following mesh current IC around? 15 ohms times IC minus IB. What's the next thing that we see? 20 ohms times IC. So when our circuit element is on the edge or the perimeter of the circuit, we're only going to have one current flowing through it. So we just have IC. What was that? 20. And then similarly, we would have plus 4 ohms IC for that 4 ohm resistor. And we set that equal to 0. So we have 4 equations and 4 unknowns. So what I would tend to do is just substitute in this IX relationship here for to put everything in terms of IA, IB, and IC. And then our next step would be to just solve this system of equations. So I'm going to throw this into my calculator as a 3 equation, 3 unknown system. So in my first equation, my coefficient for IA is 10 plus 6. My coefficient for IB is negative 6. My coefficient for IC is 0. And my constant term is positive 12 once I move that over to the other side of the equal sign. In my second equation, my coefficient for IA is -6. My coefficient for IB is going to be 6 from that leftmost term, 3 from the middle term, and 15 from the right term, right? Since 3IX is the same as 3IB minus 3IC, I have 6, 3, and 15 as my coefficients for IB. My coefficient for IC is going to be -3 minus 15. And my constant term is going to be 0. In my third equation, my coefficient for IA appears to be 0. My coefficient for IB should be -15. And my coefficient for IC will be 15 plus 20 plus 4. My constant term is once again 0. And so when I solved this system, I got IA to be 222 over 257 amps. IB was 78 over 257 amps. And lastly, IC came out to be 30 over 257 amps. So before we move on from here, if anybody else threw that system into their equation solver, did you get a similar result? Okay. So once we know these three mesh currents, we can then use them to solve for any other quantity that we might be interested in this circuit. So for example, if I wanted to know the power supplied by my dependent source, I would need to know the voltage drop across my dependent source, which is 3IX. So that would be 3 times IB minus IC. And then I would need the current flowing into the negative polarity terminal of that voltage source. What mesh current flows into the negative polarity terminal? So IB flows into the positive, so negative IB flows into the negative. And just substituting in my numbers, which one of the reasons I love the TI calculator is because it automatically stores all these things as variables. I would wind up getting negative 0.170 watts as my supplied power for that particular source. Just voltage times current flowing into the negative terminal. So before we move on to an example that contains current sources, how did you guys feel about this? Seems pretty okay. It's very similar to nodal analysis. So if nodal analysis made sense, mesh analysis should make a lot of sense. Generally speaking, it seems to me like students prefer mesh analysis a little bit more so than they do nodal analysis. I think it's just because it doesn't have fractions all over the damn place. I can't really see any other reason because they're effectively the same thing. So I'll give you the same caveat about mesh analysis that I gave you about nodal analysis in our last class video. It's an incredibly powerful tool. It is not always the best tool to use for every situation, right? So just to beat this horse straight to death, my personal process is always look for KVL, KCL, and Ohm's law relationships first, then then voltage division and current division, and then finally nodal or mesh. One of the questions that I get asked the most about when to use nodal versus is when to use nodal versus mesh, okay? Because both of them are incredibly powerful tools and both of them can solve practically every system for every piece of information that you're interested in. So my short answer is, if my system has 6 nodes, but only 2 or 3 meshes, I'm obviously going to want to do mesh analysis because I'm going to get a smaller system of equations, which means I'm less likely to make a mistake. okay? So whichever one gives me the smallest system is the one that I typically wind up using. If I have a system that I'm going to wind up with a 3-equation, 3-unknown system either way, then I might look, and if I'm trying to solve for a voltage, I'd probably use nodal analysis. If I'm trying to solve for a current, I'd probably use mesh analysis, because nodal returns voltage values and mesh returns current values. So that's my thought process for which methodology to choose. Okay, so since you guys aren't asking any questions of me, let's break things with a current source, or 2 or 3. Okay. So here I have an 18-volt source. Let's put a 10-ohm resistor here. I'm going to give myself a dependent current source here. So let's make this 4 Vx current. Actually, let's make that 1/4 Vx, just because I'm worried about that being ridiculously large and giving us weird values. Let's make this guy a 6-ohm resistor. This guy an 8-ohm resistor. Let's make this guy 15. I'm going to put a short across there. Let's say this is a 20-ohm resistor. And I also have a 2-amp source like so. And let's make the voltage Vx be, let's make it challenging. The voltage between these 2 node points in our circuit. So whenever we have current sources in our system, we are essentially going to have to adapt our nodal analysis technique we learned a moment ago to be able to incorporate current sources, okay? So I'm going to get into the technique here in a minute, but I'm just going to take a moment here and explain essentially what the problem that a current source poses is, okay? So if we had, let's call this mesh current down here IC, right? If we were trying to write our Kirchhoff's voltage law equation for IC, I'm not going to write this down because we're going to run into an issue. What would that KVL equation look like? So follow this starting from the bottom left-hand corner and go around the loop. So the first thing we would see would be the 15-ohm resistor. And so we would have 15 ohms times the total current. What's the next thing we see? That current source, right? So that is a current source, which means it is supplying some fixed amount of current regardless of whatever voltage appears across it. Okay, so we've run into a little bit of a problem because there's no way to express that voltage, the voltage drop across that current source in terms of our mesh currents, because there's no resistance relationship or anything like that that we can exploit. So instead, anytime that we have a current source, we are going to have to come up with a current relationship equation, okay? Much like every time we had a voltage source in nodal analysis, we needed a voltage relationship equation. And in special cases, we are also going to have what's called a KVL at a super mesh situation, okay? So now let me explain very briefly when we're going to have super meshes and when we aren't. If a current source is on the edge of the circuit, we will not have a super mesh, okay? We will only have a current relationship equation. If a current source is on the interior, so meaning it's shared by multiple meshes, we will have to do a KVL equation as well, okay? And so I'll show what that KVL equation is going to look like here in just a moment when I finish setting this guy up, okay? So let's call this guy mesh current IA, and let's call this guy over here mesh current IB. So running through steps, we have steps 1 and 2 already completed. We have identified and labeled our mesh currents. Step number 3 will still be to express our controlling variables in terms of our mesh currents. In this particular case, we're trying to express that voltage Vx in terms of our mesh currents, and I have intentionally given us one that's a little difficult to sort out. Okay? So instead of doing something easy, like the voltage drop across a resistor, I have this open circuit voltage here, okay? So before I tell or show you guys how to do it, does anybody have any thoughts on what we might do? Carter.
Since the 15 ohm resistor and a 20 ohm and the 2 amp resistor are in parallel, we share the same voltage, right?
So the 15 ohm resistor is not in parallel with the 20 ohm resistor. So the 15 ohm resistor is from that leftmost node over to the rightmost node. The 20 is from that leftmost node, so that one is shared. But then there's that node at the bottom middle that is not connected to the node on the right. So the 15 and the 20 are not in parallel. The 2 amp and the 15 ohm resistor are also not in parallel for similar reasons. Matthew.
Try to reconcile that something we have a 15 ohm series with 20 ohm. And those, and that equivalent resistance would be in parallel with short circuit, 0.
So the 15 ohm resistor is not in series with the 20 ohm resistor because there is a branching path off to the top that contains that voltage source and the remainder of the circuit. Teresa. So I didn't quite follow what was going on there, but I can kind of definitively say no, because you said Vx is equal to IC plus something. Vx is a voltage, IC is a current, so how can voltage equal current plus something else? So what we're going to have to do here is we're going to have to do a KVL loop in order to sort this out, okay? So this isn't really following around any mesh current per se, but we would need to do KVL around this path, right? So I'm going to erase this Vx is equal to anything, and we're just going to write a KVL equation around this guy real quick, and then we'll rearrange that and solve for Vx, okay? So what's the first thing that I see here? The 15 ohm resistor. Now that I have all of my mesh currents well defined, how would I express the voltage drop across that 15 ohm resistor when I'm going in the direction I've indicated with that gray path? So IC minus IA times 15 ohms. Absolutely right. So we have IC minus IA times 15 ohms. Then I see the voltage Vx as I go across that middle part, right? Nothing remotely wrong with that. Kirchhoff's voltage law is just us adding up voltages, and we have a defined voltage across that open circuit, Vx, the thing that we're interested in. What do we see next? The 20 ohm resistor, and what's the current flowing through the 20 ohm resistor following that direction? Positive IC. Is equal to 0. And so we could then rearrange this guy, and we would find that Vx is going to be equal to 15 ohms times IA minus IC minus 20 ohms times IC. To be clear here, I could have written that first term as negative 15 ohms times IC minus IA, but I don't like having too many negative signs all over the damn place. So when I swap those two currents around, that's the same thing as multiplying by -1. Yes, ma'am. Yeah, exactly right. So in this case, my controlling variable was that voltage Vx, so I needed to come up with a way to express that voltage Vx in terms of my mesh currents. In our previous example, our controlling variable was a current, so it was just the difference of the two currents. So the controlling variable equation is going to change for literally every single circuit, and it is dependent on the circuit itself as well as whether or not we're looking for a voltage or a current. Okay, so before I move on from this, I 100% understand that that was probably a difficult example, but does what I did to solve for that voltage Vx make sense? We've technically been doing loops like that since the third day of class. All right, so step number 4. We are going to write current relationship equations for each current source, or let's just say for all current sources. Okay. So let's start with that 1/4 Vx current source in the top middle. So I'm going to write this current relationship equation exactly how I wrote my equation for my controlling variable in the previous example. So I'm really just looking for which mesh current is in the same direction as the current source. It gets a plus sign. Which mesh current is in the opposite direction of the current source. It gets a minus sign, right? So this this current source is between meshes A and B. So those are the only two currents that I need to consider. So which one is in the same direction? IA, okay? So we'll have 1/4 Vx is equal to IA, and by process of elimination, which mesh current is in the opposite direction of our current source? IB. Great job, Teresa. So before we move on from this one, and I know I have another current source here to do in a moment, does anybody have any question, comment, or concern about how we came up with that relationship? Okay. So the last current source that we have to take into account is that 2 amp source, right? So what do you guys think the answer for this guy is going to be? So I'm going to give you a hint. Since that current source is on the edge, it will only have one mesh current associated with it, okay? So it's on the edge of mesh C. So really, it's either going to be plus IC or minus IC, depending on if IC is flowing in the same direction or the opposite direction as it passes through the branch that contains the current source. So is IC positive 2 amps or is IC negative 2 amps? Negative, right? IC, as it flows through that bottom branch, is flowing from right to left. The 2 amp current source is flowing from left to right. They're in opposite directions. We need a negative sign. Okay, so step number 5 is going to be to write a KVL equation for each super mesh. Okay. So let me more clearly define what a super mesh is, okay? So a few minutes ago, I told you guys that anytime we have a current source that is shared by multiple meshes, we are going to have a super mesh. Well, a super mesh is just the path that includes those 2 meshes and avoids taking the voltage drop across that particular current source. So in our case, our super mesh is going to be super mesh AB because our current source is between meshes A and B. And we're looking for the smallest possible path that we can take that includes those meshes and avoids that current source. So that's going to look something like this. So if I write a KVL equation around this path, essentially what I'm doing is I'm writing a KVL equation around mesh A. I'm writing a KVL equation around mesh B, and I'm adding those 2 guys together because 0 plus 0 is going to be equal to 0. And the voltage drop across that current source will be counted as positive polarity on top and positive polarity on bottom. So when they get added together, they cancel out. Very, very similar to what we did with our super node relationships and nodal analysis, right? We lumped those 2 nodes together so that we could avoid having to include the currents that were flowing through a voltage source, which couldn't be determined or couldn't be defined in terms of our nodal voltages, but we knew they were going to cancel out. We've got the exact same situation here. We're lumping 2 meshes together to avoid having to add voltages that we can't express in terms of our mesh currents because they're just going to wind up canceling out anyway. Okay. So I want to be clear about this. We are not defining some new current whatsoever. When we're on the left-hand side of this thing, we're following mesh current IA around. And then when we're on the right-hand side of this thing, we're following mesh current IB around. So we're not making up anything new. We're not introducing any new variables. We're just lumping these guys together and skipping that branch in the middle because it contains a current source that we can't really do anything with. So what should my KVL equation look like? Yeah, so start me off with a number. Negative 18, sorry that you can't see it, yeah, but negative 18 volts. What's going to come next? 10 ohms times IA. What comes next? All right. What comes next? 8 ohms times IB. And what comes next? 15 ohms IA minus IC. Great job. Is equal to 0. And there's our KVL equation for our super mesh. Since we only have the one super mesh, that's going to be our only equation. Step number 6 is going to be write a KVL equation for any remaining meshes that don't contain a current source. So in this particular example, there aren't any. I could force one to happen if I gave myself another mesh around the right-hand side or something like that, just for the sake of argument, but I really don't think it's necessary. This is an algorithm, and if the conditions do not apply, then we should just skip that step, right? So if we don't have a dependent source, we would obviously skip step 3 because there are no controlling variables. So I don't see any reason to just make this harder for the sake of it being harder, okay? So for this particular circuit, we have all of the information that we need, and we should be able to see that pretty easily because we have 4 different variables, right? We have our 3 mesh currents, IA, IB, and IC, and we also have that unknown voltage Vx. How many equations do we have? Here's 1, 2, 3, and 4. We don't need any more equations to solve this system. We're good to go. So step 7 is just solve this thing. So you all should be familiar with your calculators to be able to, so this is 4 equations, 4 unknowns, but we could pretty easily, if we were so inclined, express, so we could substitute in this Vx equation right here for this Vx right here, and we have a 3 equation, 3 unknown system that we could solve with our calculators, right? So I'm not going to bother with actually solving this system to get numerical answers or anything. The process is what's important here. The last thing that I want to show you guys is what happens if we have multiple current sources in a slightly different configuration that we have here. It's a little bit harder to explain without just showing you an example. So let's say that I had a system like this. So here's a 10 ohm resistor, a 5 ohm resistor, a 3 amp source, 20 ohm resistor, two amp source, and maybe a 15 ohm resistor. Over here, right? Step 1 and 2, we would define our, or identify and label our mesh current. So there's, let's call it IA. Here's IB. And here's IC like so. Step 3 has to do with controlling variables. There are no dependent sources, so we don't have to do that step at all. Step 4 is our current relationship equations. So what are our current relationship equations going to be for this circuit? So let's start with the 3 amp source. So how would I express that 3 amp source in terms of my mesh currents? What was that, Mr. Maestri? Which mesh current's flowing in the same direction? IB. Which mesh current's flowing in the opposite direction? So IB minus IA. How would I do that for my 2 amp source? IB minus IC. All right. So in this case, I have 2 interior current sources. So I'm going to have 2 super meshes, but I'm going to lump them together as one super mesh effectively. Okay. So you could call it a super duper mesh if you were so inclined, whatever floats your boat. But essentially, my smallest path that I can take that avoids taking the voltage drop across both current sources is just applying KVL around the perimeter of the circuit. So what would that KVL equation look like? Plus, plus, plus is equal to 0. 3 equations, 3 unknowns. I'm done. Now, let me break this. What if this 15 ohm resistor over here were another current source? I'd have a third current relationship equation. So what would that look like? 1 amps is equal to negative IC. Can I write the KVL equation for this system? Not at all, but I don't need to. I have 3 unknowns and 3 equations, right? So essentially, if I combine super meshes and I always wind up with a situation where I've got a current source on the perimeter that's preventing me from writing a KVL equation, that's perfectly okay. It will be handled by all of the current relationship equations associated with that super duper mesh or whatever, okay? You're going to see something like that in the last problem of this in-class assignment. So I just wanted to make you aware of what was going on before all of you harassed me about what was happening. Now only half of you will harass me about it, which is fine. So unless anybody has any further questions, I'd like for you guys to get working on your ICA for today.